Okay, this is a video on exponential and logistic modeling. So we've just talked about exponential and logistic functions. So now we're going to talk about how to fit them in a model. So here you're going to see some of the information you need to fill in on your notes there. So an exponential population model is for the situation where we have a population, which we call capital P. It's changing at a constant percentage rate per year, then we can use this formula. So this is what you fill in your box. So it's P of T equals P naught, or P sub 0, times 1 plus R to the T. And P naught is the initial population. So P sub 0, that's where we start at the beginning. And R is expressed as a decimal. So if you talk about 20%, then that means 0.2 for a decimal, and then T is the time in years. If R is greater than 0, then we say 1 plus R is the growth factor. And if R is less than 0, then we have a decay factor for the population. Okay, so that's how we do the difference in growth and decay. All right, so here's the first example. We're going to say whether this population is exponential growth or exponential decay, and then find that percentage of growth or decay. So on this first example, we can see it fits the format where inside the parentheses is 1 plus R, and that equals 1.025, which if we think about in percentages, this would be, or think about it's 1 plus your rate, 0.025. Well, in percent then, if R is 0.025, we move it 2 decimal places, and that would be 2.5% growth because it's positive. So that's your R, because it's 1 plus R inside. Then for this one, we have that 1 plus R equals what's inside there, which is 0.92. So that means it's 1 minus something in order to get 0.92, because it has to be either 1, it's 1 plus R or 1 minus R. Well, in this case, it's minus, and it's 1, which is 100%, minus 0.08, which in percentages is 8%. So you're going to have 8%, and then it's decay. So that's your decay factor. So if it's less than 1, like 0.92, it's like saying every year we're multiplying by 0.92. So since it's a number between 0 and 1, you're going to get it to get smaller. So you're taking, say, the 92% of the population from the year before, so there will be less. All right, so now we're going to determine the exponential function that has these things. So we have an initial value of P sub 0 is 12, and it's increasing at a rate of 6% per year. So first thing, always good to do, especially when you're learning a new formula, is to write the formula down. So this is the formula that we just wrote. And then we would fill in everything we know. So instead of P sub 0, we put 12. That's the initial value. And it's 1 plus the rate of 6%, which we're going to use a decimal for that, which is 0.06, raised to the T. And then the final way we might want to write that is go ahead and add together that 1 plus 06 as 1.06 to the T. So that would be our equation that models that situation. Okay. So now we're going to talk about another example, and we're going to solve it algebraically, which is going to remind us how to do some things from Algebra 2 about solving with exponentials, but we're going to review that also. So don't worry too much if you can't remember everything there is about how to solve one of these equations. So we suppose that we have a culture of 100 bacteria in a petri dish, and the culture doubles every hour. Predict when the bacteria will equal 250,000. So we have the formula. So we have PT equals P sub 0, 1 plus R to the T. So we're going to fill in the situation that we have. Well, we want to know when we have 250,000. We want to know when is that the population. And our initial value is 100. We started with 100 bacteria. It doubles every hour, which means R is actually 1 or 100%. So 1 plus R is 2. You could actually figure that out without having to know that it's growth, because obviously when something doubles, you multiply it by 2. So you're just going to keep multiplying by 2. So that fits your exponential there. So to solve this algebraically, we're going to first get the exponential part all by itself. So we're going to divide both sides by 100. Well, when you divide by 100, of course, when you divide by and things end in zeros, you're just getting rid of those zeros. So this is going to be 2,500 equals 2 to the t, because those zeros are going to go away when you have powers of 10 like that. Now to solve this, so again, maybe something you don't remember from Algebra 2, so just learn it here a little bit, and then we'll learn more later. So to solve this, we're going to apply the inverse function, or an inverse-like function, I guess, to both sides. So inverse of an exponential is a log, so we're going to do the ln of both sides, because it actually is usually... we just almost always use base e. So we almost always use ln to solve it. And then one of the properties of logs that you would have learned last year, that again we will review, is that the reason this is such a good way to solve it is that a rule for logs is that that power can go out in front. So now I have t times ln of 2 equals ln of 2,500, and I want t by itself. So I simply divide both sides by ln of 2. So I get ln of 2,500 over ln of 2. And if I put that in the calculator, so it would be good to practice that, I get that t is about 11.287. And then remember to put units. It's in hours if we read the problem again. So don't stress too much over the algebraic solving. They'll all be really simple like this, and follow this basic process until we get to more on that. Now another way to solve it would be to solve it graphically. So we'll go ahead and do this on the calculator, but that's what you're going to end up with so that you can see what you get there. So we're going to add a graph page, and then we're going to graph both functions. So first I'm going to graph 100 times 2 to the x, and then I need to graph 250,000, because that's what I want to see the intersection on, which of course I can't see, but I know that y is 250,000, so I know that I can change this y value to something bigger than 250,000, so I'm going to pick 300,000, and then I can see where they intersect, kind of. I can see that it's over to the right, so remember we can grab a hold and scoot it over, and now I can see that intersection, and I want to go find that intersection, so that was menu, and then analyze graph, intersection, and I just make sure I'm lower, which right there I am, and then I select that, and now it asks for upper bound, so I just drag across, and then I hit enter, so it sticks on here, and then I'm going to grab it and I'm going to move it so I can see it, and then there's my answer. And then don't forget, it's going to give you often scientific notation, so don't ever write on a piece of paper your answer is 2.5 e plus 5. This means times 10 to the 5th. So you take 2.5 times 10 to the 5th means move the decimal 5 places to the right. So that 2 was already there. Now I'm going to move the decimal. So there's 1 place, 2, 3, 4, 5. Now we already knew that was the y value where we intersected, of course, because we made the problem that way, but still good to see that. And then we see that we have 11.3. We can get more decimals in several different ways, which ask about that if you don't remember, because we've talked about that in class several times. So same idea as the graph that's right here. This setting allowed the graph to have more decimal places. I don't like to change that as a default just because I don't want them all the time. So we've talked about ways to get those. Okay, so now let's talk about modeling what's called radioactive decay. So we're going to suppose that we have a half-life of a substance that's about 40 days, and there are 8 grams present initially of this substance. So a half-life means every 40 days, half of the substance is gone. So there's always something left, but half of it's gone. We want to find the time when there will be 1 gram remaining. So let's get to our equation and then we'll see. Oh, I guess we can't see it from there. So we want to look and figure out how we got to this picture. So I'm going to move it actually out of the way. So we want to remember that we have that equation, and we know that if you plug in 0, we get 8. So that means that initial condition, and we know that it's decay, and the base is 1 plus R, but it's decay, so it's 1 minus the rate, which is half. We have half of a life left. And so we're going to end up with the equation being 8 times 1/2, because 1 minus a half. And then your time interval is actually t over 40. And that's because t over 40 represents the number of half-lives that we have. So that's the number of half-lives. So this is what we have for our equation. And if we go put it in the calculator, which that picture is not even that one, so let's go ahead and put it in the calculator real quick. So we add a new page, we add our graph, and we're going to look at the graph of 8 times, I'm going to just use 0.5 to be quicker. It's 1/2 raised. Now here I have to use it's better to use a fraction bar. And then remember, we always use x even if the problem has t or some other variable in it, and I graph it. I can't see anything because I need to be way to the side here in order to see something. Now remember, a good strategy is just to grab and sort of move a little bit, and then sometimes you can see it. So see, I can see part of the graph. So now I can just go over and click on the X, and I can pick like, let's just pick like 150 for the value. So now I can see a little bit better what's going on here. And I want to know when, the question is, when will there be 1 gram remaining? So I'm actually looking where it intersects 1. So we can go ahead and add that, y equals 1. And so I can see where the intersection is. I'm going to kind of move this around and move these out of the way, so I can see where the intersection is, and then I can go ahead and find it. If I analyze graph, intersection, and then I see it's 120. Now our time is in days, so our answer is 120 days. Your equation has your power for the number of half-lives for that to make sense. So that's how often it changes. So we end up with that being 1 gram remains at 120 days. Okay, so make sure you practice your calculator at some point. All right, so now we have what's called uninhibited growth formula. So that's actually on your paper there. You have to fill in the box, and the uninhibited growth formula is the amount that you have left at time t is the initial amount times e to the kt where K is some constant that is greater than 0. And it says that on your paper. So if we have uninhibited growth of cells, this would be the formula. So it says a culture of bacteria follows this law. So that means we know we fit this model. If 500 bacteria are present initially, so that's going to go in place of A sub 0, and there are 800 after 1 hour, how many will be present in the culture after 5 hours? So the very first thing we do is write down what we know from the beginning. So from the beginning, we know that A sub 0 is 500. So we'll have A sub t equals 500 e to the kt. Well, the problem is what I'm needing to find is what is K for this bacteria. Everything that grows uninhibitedly like that has uninhibited growth, is going to have a different value for that constant. So the way I'm going to find that, I know the model looks like this, but I don't know what K is I'm going to use this condition that they gave me. So they're going to give me one known value, and I can use that to find out what K is. So it tells me there are 800 left, so that's 800 is your amount after 1 hour. So we put a 1 in for T, and we put 800 in for A sub T, or A of T, because that's the amount we have. So now we want to solve that. So we're going to follow what we talked about on the last problem. So we're going to divide both sides by 500. So that's going to give me 8/5. It's 800 over 500. That's 8/5 e to the k. In order to solve this, I'm going to take the natural log of both sides. And then I'm going to put the power in front because that's a property of logs. And then I'm going to divide by ln of e. But actually, I don't really need to divide by that because ln of e is 1. So I would find that out when I put this in the calculator, or I can leave this. So I can either leave this as the answer ln of 8/5 and put it in the problem, or I can take the calculator and find out that we get K to be approximately 0.47. So now all of this together implies that my actual model is 500 e to the k, which is 0.47 t. So now I just found the model that fits this situation. Now the question is, how many will be present in the culture after 5 hours? So step number 1 is going to be just to write the model down. So I just write the model, and then I think, oh wait, I don't know K. So step 2, find K. Step 3 is we write the model down. So this is how I get the actual model. For this problem, now I'm going to answer part A, which is, now that I have the model, I want to find A of 5. Because it says 5 hours, 5 is our time. So that's 500 e to the 0.47 times 5. And then we do that in the calculator, and we get that we have approximately 5,242 bacteria. And so again, a lot of this will be calculator problems. Next question says, how long before the culture contains 20,000 bacteria? Well, we just found the model. We started off by 500 of them, and then we went and found K. We found it was 0.47 times T. So this is the model. So now what we want to know is when. So we're trying to find time. So we're solving when does 20,000 equal 500 e to the k 4t. So again, I'm going to divide both sides by 500, which is going to give me 40 equals e to the 0.47 t. So 20,000 divided by 500, you just think about, kind of think about these aren't there because I'm dividing by 100 on both sides, and then 200 divided by 5. So I have this, same thing, we take the ln of both sides. Then the properties of logs say you can take that power and put it out in front of the ln. and then ln of E is 1. So we end up with 0.47t equals ln of 40, and then we divide by 0.47, so we get ln of 40 divided by 0.47. If we put that in the calculator, we're going to get t is approximately 7.848 hours. So the answer would be at about 7.848 hours, there will be 20,000 bacteria. Okay, example 6. So this is a definite calculator problem, so be sure that you have your calculator available. If you don't, pause the video and go grab it. The other ones would be pretty easy to go back and do, but this is one where we're going to use the tables and the spreadsheets and stuff, so the spreadsheet and things. So if you don't remember how to do it, you might want to practice with me. So we have a 100-gram sample of a radioactive substance. We need to figure out an exponential function that fits this data. So every week they measure the radioactive substance, and these are the numbers that we get. So we're going to go to our calculator, and we are going to add a list and spreadsheet, because that's going to be our table, and we're going to type in this data. So the first column will be week, because it's the week number, and your second one will be weight. Well, it's not going to let me type. Let me try again. Oh, guess I got to double click. Okay, W-E-I-G-H-T, and we'll make sure that's not a reserved. Remember, if anything turns bold, you can't use that at all. So now I'm just going to type in all of my values, and so you can do this right with me. I'm doing this so you can see exactly what to do. I could have stored it, but I really want you to see how to do it and remind yourself how to do this. We've done this before with linear and power functions. So now we're going to see how it will do an exponential function. Remember that when you get to the last value, you need to be sure you hit enter, or it's not really there. So we're going to fit an exponential function to the data. Before we do that, I like to go ahead and always look at a spreadsheet or a data and statistics. Look at the scatter plot so we kind of see what it looks like. Remember, at first you just get random dots anywhere, and then we have to go click to add a variable, and we want weeks to be X, and we want weight to be Y. So if you look at that, you can see that looks pretty reasonable, that it's kind of exponential. It is going down, so it's decay, and it's seems like exponential would be a reasonable fit for that. So let's remind ourselves what to do. We go to Menu, Analyze, Regression, and now we have all these choices, and you see that number 8 is exponential. So I'm going to show exponential. So here is my answer to what I get for those values. So let's go back and triple check that we entered everything correctly. I didn't even look at it, so let me just double check that I entered the values right. Okay, so everything seems to be correct. So there's our answer. Whoops, I didn't mean to add a page. I meant to go forward page. So there's our exponential function. So we can write that down on your paper there on part A. So there's the equation for the data, 102.306 times 0.869261, or 869 is fine, 0.869 to the x. Then the question is, what is the half-life of the material? So we're going to go back to our worksheet and look at the half-life of the material. So our equation, and then we're going to solve for the half-life. Well, if we started with 100 grams, that means our half-life is when we have 50 left. So this was 102 point, I've already forgotten, 102.306 and 0.869. So let's go back to this. Let's do it this way. 306 times 0.869 to the x, and we want to solve that. So now let's figure out how we're going to solve that. We could solve it algebraically, but let's also talk about how to solve it using the solver. So we go to a calculator page. So I accidentally added an extra page, so I'll just add that. So go to a calculator page. So another way to do this is to just do solve. So if it's a calculator question, I could graph it, look where it intersects. I could do solving with the solver. There's all kinds of things that I can choose to do. So what I want to solve is, when does 50 equal our 102.306 times 0.869 raised to the x, arrow out of that exponent, and then put comma x because it has to know what am I solving for, and I hit enter, and there's my answer. So I get 5.09. So let's go back to the problem. And I'm going to read the original problem real quick. Ignore that. So the original problem says that it's in the weeks. So this is at the end of the week. So that means my answer that was 5.09 is in weeks. So I got x equals 5.09. So that means in the half-life is approximately 5.09 weeks. And then we have some additional things to solve there. So let's go ahead and solve that. So this is my equation. So the next question would be virtually the same. It says, when will there be 10 grams of material left? Well, all I'm going to do is change 50 to 10. So on the calculator, that will be really easy to do. I can go up here and copy and paste and go back, and now I want to solve when is 10 equal to that. When do I have 10 left instead of 100? And so that's going to be in about 16.56 weeks. And then it says how much radioactive material will be left after 52 weeks. So now I'm actually plugging in. So 102.306 times 0.869 to the 52 now. I'm going to actually put in a number, and we see that we'll have about 0.069 grams. There's one more example on there, and we'll do that example in class, and that wasn't about logistic modeling. So we'll talk about that one next time.